Before we begin, let's slow everything down together. If you're lying in bed right now, let your body sink just a little deeper into whatever surface is beneath you. Feel the weight of your shoulders, your arms, the back of your legs, all pressing gently down, becoming heavier, softer. If you're sitting somewhere quietly, let your eyes grow heavy if they want to. There's nowhere you need to be right now. No problem that requires solving tonight. The world outside will keep its pace while you, for just a little while, drift somewhere altogether different. Take a slow, full breath in through your nose. Feel your rib cage expand, your belly rise. Hold it for just a moment, and then release it slowly, feeling the quiet that follows. Good. Once more if you like. Let every exhale carry something away with it, whatever the day left behind. Tonight we're going to travel somewhere. Not to a warm place, not to a summer meadow or a sunlit coast, but to the very edge of our solar system. We're to visit a small frozen world that has to visit a small frozen world that has spent billions of years in near-perfect stillness, orbiting patiently in the outer darkness. A world that science thought it understood, and then discovered it didn't understand at all. We're going to Pluto. And along the way, as the story of this curious little world unfolds around you, you can let your mind drift wherever it wants to go. The details will wash over you, painting pictures at the edges of sleep. Mountains of water ice rising from nitrogen glaciers, a great frozen heart visible from space. Volcanoes that erupt not with fire and lava, but with slurries of cold water ice. Slow-motion eruptions into a sky of deep blue. Let the images come and go without holding on to any of them. This isn't a story that requires you to remember anything. It's just a story told quietly for you to drift through on your way to wherever sleep takes you. So breathe one more time. Let your jaw relax, let your shoulders drop, and let's begin. Welcome to the Science Pillow. If you're new here, this channel is dedicated to one simple idea: that science is most beautiful when it's given room to breathe, when you're not rushing through it but letting it settle over you slowly, the way good stories do. Whether you're winding down after a long day, lying awake with a restless mind, or simply someone who finds that learning and relaxing can happen at the same time, this is the place for you. We cover the full sweep of scientific wonder here: the deep cosmos, the mysteries of the natural world, the strange machinery of the human mind, and the great stories from the history of discovery. Every video is written with care, every detail chosen because it's genuinely fascinating, and every sentence paced to carry you gently toward sleep rather than jolt you awake. If tonight's journey through the solar system speaks to you, please consider liking this video. It takes 2 seconds and it tells the algorithm that this kind of thoughtful, unhurried science content deserves to reach more people who might need exactly what you found here. And if you'd like to come back, to float through black holes and ancient fossils, and the chemistry of stars in future evenings, then hitting subscribe is the way to make sure you never miss another journey. But for now, there's nothing to do at all. Nowhere to click. Just settle in. Close your eyes if you haven't already, and let's drift together toward the edge of the solar system, toward the small, cold, astonishing world that science spent nearly a century misunderstanding. This is Pluto, and it is not what you think. Section 1. The world we thought we knew. There's a particular kind of nostalgia that belongs to the 9-planet solar system. If you grew up before 2006, You almost certainly had it somewhere in your life. A poster on a classroom wall, a styrofoam model suspended from a ceiling by threads, the mnemonic your teacher taught you to remember their names in order. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. 9 planets circling the sun, each one distinct, each one with its own personality. And at the very end of that lineup, small and cold and impossibly far away, was Pluto. For most of the 20th century, Pluto occupied a particular place in the popular imagination. It was the lonely planet, the outermost one, the runt of the family. Where Jupiter was enormous and terrifying and girdled with storms the size of entire worlds, where Saturn wore its magnificent rings like a jewel, Pluto was small and dim and mysterious. Not much was known about it for a very long time. It was too far away, too small, and the telescopes of the early 20th century simply weren't powerful enough to reveal anything about its surface or structure. For decades after its discovery in 1930, Pluto was essentially a dot of light in the sky, a moving speck that distinguished itself from background stars only by its slow, patient drift across photographic plates. And yet, despite being essentially unknown, Pluto was beloved. Maybe because of its smallness. Maybe because it sat alone at the edge of everything, so far from the warmth of the sun that it took light itself more than 5 hours to make the journey out to its orbit. Maybe because its name carried a certain mythology. Pluto, god of the underworld, ruler of the realm of the dead, distant and dark and dwelling apart from the other gods. There's something almost melancholy about the name, a fittingness to its position at the outer edge of the solar system, so cold and remote that it might as well be a different universe entirely from the warm, rocky worlds of the inner solar system. For 76 years, from 1930 to 2006, Pluto was a planet. Children learned its name alongside 8 others. Astronomers catalogued it, studied it as best they could with available tools, and debated its properties. Scientists gradually revised their estimates of its mass downward. In 1930, some initial estimates suggested Pluto might be similar in mass to Earth, but as measurements improved over the following decades, that number shrank and shrank until Pluto was revealed to be far smaller and lighter than anyone had imagined. By the 1990s, it was clear that Pluto was a genuinely tiny world, smaller than Earth's own moon, with a mass only about 1/500th that of Earth. And it was clearly different from the 8 planets that preceded it. Different in composition, different in orbit, different in character. Yet, still the textbooks said planet. Still the posters said 9. There's something touching about human stubbornness in the face of facts. And Pluto brought out both the best and worst of it. When the reckoning finally came, it would cause something very unusual in science. Genuine, widespread public grief over a reclassification. People wrote letters. State legislatures passed resolutions. Children sent angry mail to observatories. A word entered the English language. To be Plutoed meant to be demoted, to be diminished, to be stripped of a status you thought you had earned. But here is the quietly wonderful thing that gets lost in all of that cultural noise. The reclassification of Pluto didn't make it less interesting. In fact, it made it infinitely more interesting. Pluto was not diminished by the discovery that it was something other than a planet. Pluto was revealed as a world more ancient, more complex, more geologically alive, and more scientifically important than anyone had imagined when they thought of it merely as the 9th and smallest. planet in a well-ordered family. The story of Pluto is not a story of demotion. It's a story of discovery, of how a small dot of light seen by a young man on a cold February morning in Arizona turned out, nearly a century later, to be one of the most surprising worlds in the entire solar system. And it begins, as so many great scientific stories do, with a dream of something that doesn't yet have a name. Section 2. The Discovery, Clyde, Tombaugh, and Planet X. Percival Lowell was a man of tremendous wealth and even greater ambition. Born in 1855 into one of Boston's most distinguished families, Lowell spent the early part of his life as a businessman, before devoting himself, with characteristic intensity, to the question that would define his legacy. Was there life on Mars? Lowell constructed an observatory near Flagstaff, Arizona, in 1894, at an elevation of over 7,000 feet above sea level, where the air was clear and the seeing conditions were among the best in the country. From this perch, he made detailed observations of Mars, becoming convinced that the dark lines he saw on the planet's surface were canals, artificial waterways built by an intelligent Martian civilization struggling to survive on a drying world. The canal theory was wrong. We know that now. But Lowell's Flagstaff Observatory, the institution he founded and funded, would go on to make one of the greatest astronomical discoveries in human history, though not until 13 years after his death. Around 1905, Lowell became interested in a different problem. Astronomers had noticed what appeared to be slight anomalies in the orbits of Uranus and Neptune, tiny wobbles and deviations that couldn't be entirely explained by the known gravitational influences of the other planets. Lowell theorized that these disturbances were caused by an undiscovered planet lurking beyond Neptune, a massive body whose gravity was tugging on its neighbors from across the darkness. He called this hypothetical world Planet X. From 1905 until his death in 1916, Lowell funded an extensive search for Planet X from his Arizona observatory, but found nothing. His calculations had pointed him toward roughly the right region of the sky, but the methods available at the time simply weren't sensitive enough to detect such a faint and distant object. After Lowell's death, his widow entered into a protracted, legal dispute with the observatory over his estate, and the Planet X search languished for over a decade. Then, in 1927, the observatory's director, Vesto Slipher, secured funding to build a new 13-inch telescope, specifically designed for wide-field photographic surveys. It was time to resume the hunt. The observatory needed someone to operate this new instrument, someone with patience, good eyes, attention to detail, and a willingness to undertake the almost unbelievably tedious work of photographing the same patches of sky over and over again, and then comparing those photographs by eye, plate by plate, looking for any object that had moved between exposures. By January 1929, they had their man. His name was Clyde William Tombaugh, and he was 22 years old. Tombaugh had grown up on a farm in Streator, Illinois, and later in Burdett, Kansas. His formal education had ended at high school. A hailstorm in 1928 had destroyed his family's crops and put college out of reach financially. But Tombaugh had been fascinated by astronomy since childhood, teaching himself the mathematics of the subject from books and grinding his own telescope mirrors by hand, using parts salvaged from farm machinery, and even a crankshaft from his father's 1910 Buick automobile. He had built his own 9-inch reflector telescope, and in 1928 he made detailed drawings of Jupiter and Mars, and sent them to the Lowell Observatory in Flagstaff, hoping to receive some professional feedback on his work. Instead of a critique, he received a job offer. Tombaugh arrived at Flagstaff in January 1929. His initial duties included stoking coal stoves and shoveling snow off the observatory's telescope domes, the unglamorous physical labor that comes with any scientific operation. But within weeks, he was at the 13-inch telescope, beginning the photographic survey of the sky. His method was painstaking. He would photograph the same region of sky on multiple nights, separated by several days. Each glass photographic plate captured hundreds of thousands of stars. He would then examine pairs of plates using a device called a blink comparator, a machine that allowed him to switch rapidly back and forth between two images of the same star field. Background stars, being enormously distant, didn't move. But anything closer, an asteroid, a comet, a planet, would appear to jump between positions as he blinked from one plate to the other. Night after night, plate after plate, Tombaugh examined these images. The work was extraordinarily dull by any conventional measure. Each plate might take an hour or more to examine carefully. Stars blurred, plates streaked, optical artifacts mimicked moving objects and had to be eliminated one by one. Tombaugh was meticulous. He was precise. And he was patient in the way that only the truly dedicated can be patient, not tolerating the work but genuinely, quietly absorbed in it. The plates that would change everything were taken on January 23rd and 29th of 1930. On the afternoon of February 18th, 1930, at around 4 o'clock, Tombaugh was examining these two plates of the Gemini star field when something caught his eye. An object was moving. Not just moving slightly, but moving at exactly the speed you would expect from a trans-Neptunian planet. It was dim, magnitude 15, far too faint to see with the naked eye, and it appeared as little more than a pinprick of light. But it was there, jumping between positions in the Gemini star field, behaving in precisely the way a distant planet should behave. Tombaugh later described the moment with characteristic modesty. He walked down the hall to the director's office and announced that he thought he had found Planet X. Observatory Director Vesto Slifer, initially cautious, asked to see the plates himself. He confirmed the finding. The team took new photographs over the following weeks to verify the discovery, and on March 13th, 1930, the anniversary of Percival Lowell's birthday, and also the anniversary of William Herschel's discovery of Uranus, the Lowell Observatory announced to the world that a ninth planet had been discovered. The New York Times headline the following day read, "Ninth planet discovered on edge of solar system, first found in 84 years." The discovery prompted a worldwide outpouring of suggestions for what to name the new planet. Thousands of letters arrived at the observatory. The staff wanted a name from mythology, following the tradition of the other planets, and 3 candidates were seriously considered: Minerva, Cronus, and Pluto. Minerva was eliminated because it had already been used for an asteroid. Cronus was rejected in part because of association with an astronomer who was widely disliked and might try to claim credit for the suggestion. That left Pluto, the Roman god of the underworld, the ruler of the dark realm beneath the earth. The first person outside the Lowell Observatory to suggest the name was not an astronomer at all. She was an 11-year-old girl named Venetia Burney, living in Oxford, England. On the morning of March 14th, 1930, Venetia's grandfather, a retired Oxford librarian named Falconer Madan, read aloud from the newspaper over breakfast that a new planet had been discovered. Venetia, who had studied classical mythology and was well versed in the names of the Greek and Roman gods, immediately thought of Pluto. It seemed fitting, she said. A dark, gloomy, distant world. What better name than the god of the underworld? Her grandfather telegraphed the name to an Oxford astronomer who forwarded it to the Lowell Observatory. On May 1st, 1930, the name Pluto was officially adopted. Pluto also carried Percival Lowell's initials in its first two letters, P and L, which pleased everyone. The astronomical symbol for Pluto combined these two letters. Venetia Burney would go on to live a full and quiet life as a teacher and accountant, occasionally reminded in interviews that she had named a planet when she was 11 years old. When NASA's New Horizons spacecraft was finally launched toward Pluto in 2006, it carried a small coin commemorating her contribution. Tombaugh continued his planet search survey at Lowell for another 12 years, eventually examining more than 30,000 galaxies, nearly 1,000 asteroids, 2 comets, and numerous star clusters, all byproducts of the massive photographic survey he was conducting. He never found another planet. He went on to complete bachelor's and master's degrees in astronomy at the University of Kansas, and later built the astronomy program at New Mexico State University, where he remained until retirement in 1973. He died in 1997 at the age of 90, and some of his ashes were placed aboard the New Horizons spacecraft. Clyde Tombaugh, the farm boy who had taught himself astronomy from books and ground his own telescope mirrors from salvaged parts, became the first person to have their remains carried to the edge of the solar system. And the world he discovered? It sat patiently in the darkness for another 65 years, waiting for humanity to understand it well enough to truly see it. Section 3. A World Shrinking, The Road to Reclassification. From the moment of its discovery, Pluto was an awkward fit for the category of planet. Early estimates of its mass were wildly off. In 1930, based on the brightness of the object and assumptions about its reflectivity, some astronomers suggested it might be as massive as Earth. This number fell over the following decades as better observations accumulated. By the 1970s, astronomers understood that Pluto was considerably smaller than Earth, but the exact size and mass remained uncertain. The problem was that Pluto was so small and so distant that even the best telescopes of the era couldn't resolve it into a disk. It remained, frustratingly, a point of light. The situation changed dramatically in 1978. James Christie, an astronomer working at the United States Naval Observatory in Flagstaff, was examining photographic plates of Pluto when he noticed something unusual. Pluto's image appeared slightly elongated, as if it had a bump on one side. The bump seemed to move around Pluto over time. Christie worked out the explanation. Pluto had a moon, one large enough relative to Pluto's size to be affecting the appearance of the combined image. He named this moon Charon, officially for the ferrymen who carried the souls of the dead across the river Styx in Greek mythology, but also, less officially, because the name began with the same 4 letters as his wife Charlene's nickname, Char. Charon's discovery was transformative for our understanding of Pluto. By observing Charon's orbit, scientists could calculate the mass of the Pluto-Charon system directly using Newton's laws. The answer was startling. The combined mass of Pluto and Charon together was only about 1/500th the mass of Earth. Pluto alone was even less. Further, by watching the two bodies pass in front of each other during a series of mutual eclipses in the late 1980s, astronomers were able to determine their sizes with much greater precision. Pluto's diameter came out to approximately 2,370 kilometers, making it smaller than Earth's moon, which is about 3,474 kilometers across. A planet smaller than our moon. It was a sobering measurement. Pluto was not just a small planet, it was genuinely tiny by any standard. 7 of the solar system's moons were larger than Pluto. This didn't immediately end Pluto's planetary status, but it planted a seed of doubt that would grow slowly over the following decades. Then, in the 1990s, something remarkable happened. Astronomers using large ground-based telescopes began detecting other objects in the outer solar system beyond Neptune. Small, icy bodies occupying a vast disk-shaped region that had been theorized but never confirmed. In 1992, David Jewett and Jane Liu at the University of Hawaii made the first confirmed detection of what would come to be called a Kuiper belt object. Over the following years, the tally of these objects grew rapidly. Dozens, then hundreds, then thousands of icy bodies were discovered beyond Neptune's orbit, all occupying the same general region of space as Pluto. The implications were unavoidable. Pluto wasn't alone in its orbital neighborhood. It was, instead, the largest known member of a vast population of icy debris, left over from the formation of the solar system. Astronomers began asking the question quietly at first, then more loudly. If Pluto was simply the biggest known member of this cloud of icy objects, should it still be considered a planet? The question became urgent in 2005, when a Caltech astronomer named Mike Brown and his colleagues announced the discovery of an object they had temporarily nicknamed Xena, officially designated 2003 UB313, and later named Eris. Initial measurements suggested that Eris was not just similar in size to Pluto, but possibly larger. If Pluto was a planet, then Eris was a planet too. And if Eris was a planet, then there would have to be a serious reckoning with how many other Kuiper belt objects might eventually be recognized as planets. The number could be dozens, perhaps hundreds. The solar system could have 150 planets or more. The International Astronomical Union, the organization responsible for officially defining and naming objects in the solar system, decided it needed to draw a line. In August 2006, at their General Assembly in Prague, the IAU convened to vote on a formal definition of the word planet. It was the first time in history that planetary scientists had attempted to codify this definition precisely, and the process was contentious from the start. 4 separate proposals were considered over 8 days of debate. The one that ultimately passed defined a planet as an object that orbits the Sun, has sufficient mass for its self-gravity to have pulled it into a roughly spherical shape, and has cleared the neighborhood around its orbit of other objects of comparable size. Pluto met the first 2 criteria, but the third, clearing its orbital neighborhood, it definitively failed. Pluto shared its orbital region with thousands of other Kuiper belt objects, none of which it had cleared away or gravitationally dominated. Under this definition, Pluto was reclassified as a dwarf planet, a member of a new category that also included Eris, Ceres, and several other bodies. The vote was not unanimous. Only 424 astronomers were present to cast ballots out of an estimated 10,000 professional astronomers worldwide. Many prominent scientists were absent, either unwilling to attend or unaware that such a consequential vote would be held. Alan Stern, the principal investigator of NASA's New Horizons mission, which had been launched earlier that year and was already flying toward Pluto, was furious. He called the definition unworkable and absurd, pointing out that under a strict interpretation of clearing your orbital neighborhood, even Earth could be said to fail, given that it shares the inner solar system with asteroids that cross its orbital path. He began circulating a petition protesting the decision. More than 300 scientists eventually signed it. Owen Gingerich, the Harvard astronomer who had led the original committee tasked with creating a planet definition, called the final result confusing and unfortunate. Other scientists noted that the entire concept of clearing the neighborhood was poorly defined. What exactly did clearing mean, and to what degree did it need to be accomplished? The public reaction was something else entirely. People who had grown up with 9 planets felt genuinely, personally affronted by the change. Schools scrambled to update their materials. Museum displays were revised. Planetariums updated their programming. The American Dialect Society voted Plutoed as the word of the year for 2006, meaning to demote or devalue someone or something as Pluto had been demoted. The state of New Mexico passed a resolution declaring that Pluto would always be considered a planet within New Mexican skies. Illinois, where Clyde Tombaugh was born, passed a similar resolution in 2009. Arizona, where Pluto was discovered, did the same in April 2024. None of these resolutions changed the science, but they said something genuine and human about the attachment people form to things they grow up with, to the cosmological furniture of their childhoods. Pluto had been there in textbooks and on posters for 3 generations. Losing it felt to many people like losing something real. But the truly remarkable thing, the thing that makes Pluto's story not a tragedy but a triumph, was waiting just 9 years away, on a spacecraft already speeding through the darkness. Section 4. The Kuiper Belt, Pluto's True Kingdom. To understand what Pluto actually is, you first need to understand where Pluto lives. Beyond the orbit of Neptune, at a distance of roughly 30 astronomical units from the Sun, where 1 astronomical unit equals the distance from the Earth to the Sun, about 93 million miles. The solar system doesn't end. It opens up into something vast and ancient and largely invisible to the human eye, the Kuiper Belt. Imagine the inner solar system as a city, dense, active, full of traffic. Rocky planets, iron core asteroids, dust clouds, and the massive gravitational dominance of Jupiter, all crowding into the relatively small region within about 5 astronomical units of the Sun. Then imagine the outer solar system, from Jupiter outward through Saturn, Uranus, and Neptune. The gas giants, enormous and magnificent, their gravity dominating everything within their reach. And then, beyond Neptune, the city thins out entirely. The traffic disappears. The roads go from busy highways to empty back roads, and then to bare terrain. And scattered across this bare terrain, extending from roughly 30 to 50 astronomical units from the Sun, are millions upon millions of small, cold, icy objects. This is the Kuiper Belt. The Kuiper Belt is not the asteroid belt scaled up. It is something fundamentally different. The objects that populate it are not primarily rock and metal, as most asteroids are, but ice, water ice, nitrogen ice, methane ice, carbon monoxide ice, ammonia ice. They formed in the frigid outer reaches of the solar system's protoplanetary disk about 4.5 billion years ago, in the first few million years after the Sun ignited. They are, in a very real sense, the leftovers from the formation of the solar system. Material that never quite coalesced into a planet, scattered by the gravitational influence of the giant planets into the vast ring of debris that orbits beyond. Neptune today. The Kuiper belt's existence was theorized long before it was confirmed. In 1943, the Irish astronomer Kenneth Edgeworth speculated that there ought to be a population of objects beyond Pluto's orbit. In 1951, the Dutch-American astronomer Gerard Kuiper published a paper arguing for something similar, a disk of icy bodies in the outer solar system. The region bears his name today, though Edgeworth's contribution is remembered in the alternate designation Edgeworth-Kuiper belt. The theoretical case was well established, but actually detecting these objects required patience and the right telescopes. That confirmation finally came in 1992, when David Jewett and Jane Liu discovered the first confirmed Kuiper belt object using a telescope at the University of Hawaii. That object, designated 1992QB1, was a reddish chunk of ice and rock about 250 kilometers across, orbiting about 44 astronomical units from the Sun. Within a few years, the floodgates opened. Hundreds, then thousands of Kuiper belt objects were catalogued. Today, astronomers estimate there are likely hundreds of thousands of objects in the Kuiper belt, with the diameters greater than 100 kilometers, and perhaps millions if you include smaller ones. They range in color from white to bright red, depending on their surface compositions and how much chemical processing they've undergone from cosmic radiation over billions of years. Pluto sits firmly in the heart of this population. It is, unquestionably, the largest known object in the classical Kuiper belt, about 2,376 kilometers in diameter, larger than any other Kuiper belt object yet discovered. Though Eris, which occupies a different orbital region called the scattered disk, is slightly more massive, despite being a touch smaller in diameter. Pluto's orbit is characteristic of a class of Kuiper belt objects called Plutones, objects locked in a 2 to 3 orbital resonance with Neptune, meaning they complete exactly 2 orbits of the Sun for every 3 that Neptune completes. This resonance is what has kept Pluto gravitationally stable for billions of years, despite the crossing orbital paths it has with Neptune. Seen through this lens, Pluto is not a failed planet that got demoted. Pluto is the king of the Kuiper belt, the largest, most complex, most geologically active member of this vast population of ancient, icy worlds. It orbits in a ring of cousins, surrounded by remnants of the solar system's birth. When astronomers discovered Eris and its companions, they didn't reveal that Pluto was small and unimportant. They revealed that Pluto belonged to a rich ancient community, the first member of this community to be discovered, the prototype for a whole new class of world. Pluto's orbit is not a tidy circle like Earth's. It is an ellipse, stretched and tilted relative to the plane in which the other planets orbit. At its closest approach to the Sun, called perihelion, Pluto comes as close as 30 astronomical units, almost as close as Neptune itself. At its farthest point, aphelion, it retreats to nearly 50 astronomical units, where the Sun is so distant and faint that it provides less than 1,000th of the light it shines on Earth. A single orbit around the Sun takes Pluto 248 years. From 1979 to 1999, Pluto was actually closer to the Sun than Neptune for a 20-year period, though their tilted orbital planes meant there was never any risk of collision. The temperature on Pluto at its surface averages around -230 degrees Celsius, or negative 380 degrees Fahrenheit. To put that in perspective, the coldest temperature ever recorded on Earth's surface was about negative 89 degrees Celsius at the Soviet Union's Vostok station in Antarctica in 1983. Pluto is nearly 3 times colder than the coldest place on Earth. At these temperatures, nitrogen, which forms most of Earth's atmosphere, is a solid, lying on the surface as frost. Water ice is rock-hard, as rigid and unyielding as granite. Methane crystallizes. Carbon monoxide freezes. Even simple gases become landscape. This was the world that NASA decided to send a spacecraft to visit. And the spacecraft they sent, a piano-sized probe called New Horizons, would transform our understanding of Pluto more profoundly than anyone had dared to hope. Section 5. New Horizons, 9.5 years to the edge. The New Horizons mission had a complicated birth. Alan Stern, the mission's principal investigator at the Southwest Research Institute in Boulder, Colorado, had been advocating for a Pluto mission since the early 1990s. Multiple proposals were submitted to NASA over the years, and multiple times the money was cut or the mission was canceled. There was a persistent sense within some quarters of the agency that Pluto wasn't worth the expense. It was small, it was dark, it was far away, and the expected scientific return seemed modest compared to the cost and the time required. But Stern persisted, and eventually, in 2001, NASA selected the New Horizons mission. The spacecraft was designed by the Johns Hopkins University Applied Physics Laboratory and built over the following 4 years. On January 19, 2006, just 7 months before Pluto would be reclassified as a dwarf planet, New Horizons launched from Cape Canaveral atop an Atlas V rocket. It was the fastest spacecraft ever launched from Earth at that time, departing at a velocity of approximately 47,000 miles per hour. Even at that extraordinary speed, the journey to Pluto would take more than 9 years. The spacecraft was small, piano-sized as NASA scientists loved to say, weighing about 478 kilograms at launch. It carried 7 scientific instruments: cameras for visible light and infrared imaging, spectrometers for analyzing surface and atmospheric composition, instruments for studying the solar wind and dust environment, and a radio receiver for studying the atmosphere during occultation. It also carried a modest collection of symbolic passengers: a small container of Clyde Tombaugh's ashes, a 35-cent stamp from 1991 bearing the legend, "Pluto Not Yet Explored," a CD containing the names of 434,000 people who had submitted their names to be included, and an American flag. The journey was not uneventful. In February 2007, just 13 months after launch, New Horizons swung past Jupiter for a gravitational assist. A precisely calculated flyby that used Jupiter's enormous gravity to fling the spacecraft onto a faster trajectory toward the outer solar system, adding about 9,000 miles per hour to its velocity. During this flyby, the spacecraft turned its instruments on Jupiter and its moons, returning remarkable images and data as a kind of trial run for the main event years ahead. Then New Horizons fell into a kind of deep slumber. For most of the 9-year journey, the spacecraft was placed in hibernation mode, a power-conserving state in which most systems were shut down, with only basic navigation and monitoring functions kept active. Mission controllers at the Johns Hopkins Applied Physics Laboratory received weekly electronic check-ins from the spacecraft, simple signals confirming that everything was working. Each week a green light. Each year the distance, too, Pluto decreased. Each year, the mission crept closer to its purpose. By early 2015, with Pluto a few months away, the excitement at Mission Control was barely contained. New Horizons began waking up properly, warming its instruments, preparing its cameras. The images arriving from Pluto were still blurry at first, just a smear of light and dark on a pale disk. But they were already revealing hints of things nobody had expected. A bright region, a dark region, a heart-shaped marking. What were these? Nobody knew yet. The mystery deepened as the images slowly sharpened. Then came the scare. 10 days before closest approach, an overloaded computer caused New Horizons to flip into safe mode, a protective state in which non-essential functions shut down and the spacecraft waited for instructions from Earth. For 2 tense hours, the team at Mission Control couldn't reach the spacecraft in the normal way. When contact was restored and the problem was identified and fixed, people wept with relief at their consoles. The mission that had taken decades to develop and 9 years to travel to its destination had come within hours of missing its narrow window. At 11:49 UTC on July 14th, 2015, a Tuesday, New Horizons flew within 12,472 kilometers of Pluto's surface. It was moving so fast that the entire encounter lasted only a few hours. During those hours, with its high-gain antenna pointed away from Earth so it could gather data, the spacecraft was incommunicado. Mission controllers at Johns Hopkins could do nothing but wait. They had calculated the exact moment when the spacecraft should emerge from its data-gathering pass and phone home. When the signal finally came through, right on schedule, people stood and cheered. But the data itself would take more than a year to fully transmit back to Earth. Radio signals travel at the speed of light, and light takes 4 hours and 25 minutes to cross the distance between Pluto and Earth at the moment of the flyby. The connection was slow by any standard, transmitting data at the rate of about 1 kilobit per second, comparable to an old dial-up modem. The full dataset from the flyby, about 50 billion bits, or roughly 6 gigabytes, didn't finish transmitting until October 2016, 15 months after the flyby. What that data contained would rewrite the textbooks, not update them. Rewrite them. Because the Pluto revealed by New Horizons was not the cold, dead, geologically inert ball of ice and rock that scientists had expected. It was something else entirely. Something more ancient and more alive, more complex and more surprising than anyone had dared to imagine. Section 6. The Heart of Pluto. Sputnik, Planitia, and a Living World. Even before the flyby, the images New Horizons returned during its approach had revealed something extraordinary. On one side of Pluto, in the equatorial region, there was a large, bright, unmistakably heart-shaped marking. It appeared as New Horizons was still 5 million miles away. A luminous shape against Pluto's darker surface, roughly 1,000 miles across, gleaming with reflected sunlight. The science team informally called it Tombaugh Regio, in honor of Pluto's discoverer. And within that heart-shaped region, as the images sharpened on approach, they could see that the two lobes of the heart were quite different from each other. The eastern lobe was darker and more complex, covered with craters and varied terrain. But the western lobe, later given the official name Sputnik Planitia, honoring Earth's first artificial satellite, was something else entirely. It was smooth, unnervingly, strikingly smooth, almost perfectly flat, stretching across a vast area with no impact craters visible at all. The absence of craters is enormously significant to planetary geologists. Craters accumulate over time as meteorites and other space rocks strike a surface. A heavily cratered surface is an old surface, one that has been sitting unchanged for hundreds of millions or billions of years, faithfully recording every impact. A surface with few or no craters is a young surface, one that has been resurfaced recently enough that any earlier craters have been obliterated by whatever geological process is ongoing. The complete absence of visible craters on Sputnik Planitia means its surface is geologically very young. Estimates suggest perhaps only a few million to a few 100,000 years old. Some calculations put the age of the youngest parts of Sputnik Planitia at as little as 180,000 years. In the context of a solar system that is 4.5 billion years old, 180,000 years is yesterday morning. This is a surface that is essentially being renewed as we watch. What is doing the renewing? The answer is one of the most remarkable geological processes discovered in recent decades: convection of frozen nitrogen ice. Sputnik Planitia is a basin, likely the remnant of an enormous ancient impact, roughly 1,000 kilometers wide and several kilometers deep below the surrounding terrain. Over time, this basin has filled with nitrogen ice, carbon monoxide ice, and methane ice. These ices are not the rigid, immovable substances you might expect at these temperatures. Nitrogen ice, under the conditions prevailing on Pluto, is actually somewhat plastic. It can flow slowly, the way glaciers on Earth flow, but on timescales of millions of years rather than thousands. But even more dramatic is what happens below the surface of Sputnik Planitia. The rocky interior of Pluto generates some residual heat through the radioactive decay of elements in its core. The same process that keeps Earth's interior warm, just operating on a smaller scale. This faint heat, conducted upward through the icy crust, warms the bottom of the nitrogen ice layer slightly, making it less dense than the cold ice above. The warmer, lighter ice rises. The colder, denser ice sinks. The result is convection. Slow, organized circulation cells of ice, blobs of material cycling continuously up and down through the ice layer. These convection cells are actually visible in the New Horizons images. Looking down on Sputnik Planitia, you can see that the surface is organized into a pattern of irregular polygonal cells, each one roughly 20 to 40 kilometers across, separated by slightly darker troughs at their boundaries. Each cell is a single convection plume, a rising column of slightly warmer ice that spreads out at the surface and then sinks back down at the margins. The turnaround time for a single convection cycle is estimated at roughly 500,000 years. The heart-shaped region also forced a remarkable rethinking of Pluto's history. Sputnik Planitia is full of nitrogen ice, and nitrogen is denser than the surrounding water ice crust. This mass concentration has had a remarkable effect. It has caused Pluto to physically reorient itself, to wobble and shift its orientation relative to its moon Charon. The technical term for this is true polar wander, and it means that the location of Sputnik Planitia on Pluto's surface today, directly opposite the side that faces Charon, is not an accident. Pluto rotated until this massive, icy basin was in the gravitationally stable position facing away from Charon, like a ball rolling until its heaviest point is at the bottom. This is a planet-scale rearrangement of orientation, driven by the weight of a basin of ice. Beyond Sputnik Planitia, the landscape of Pluto revealed by New Horizons was staggeringly varied. At the margins of the nitrogen glacier there are mountains, not metaphorical. mountains or gentle hills, but genuine, towering mountain ranges made of water ice. Peaks rising up to 3,500 meters, comparable to the Rocky Mountains of Colorado. These mountains stand at the edge of Sputnik Planitia, like a frozen shore, their summits occasionally dusted with methane frost that condenses out of the thin atmosphere as temperatures vary. The mountains are made of water ice, which at Pluto's temperatures is as hard as rock and can sustain the stress of towering peaks. There are also, remarkably, dunes, sand dunes on Pluto. Discovered in the New Horizons images, the dunes stretch across at least 75 kilometers of the western edge of Sputnik Planitia, near the base of the surrounding mountains. Instead of sand, they are made of tiny particles of methane ice, each grain perhaps the size of a sand grain on Earth. They form through an aeolian process, the same wind-driven mechanism that creates dunes on Earth and Mars. With Pluto's thin, wispy atmosphere, only 100,000th as dense as Earth's, generating enough wind to transport these particles and pile them into ridges. The dunes are young, geologically speaking, estimated to have formed on timescales of decades to centuries. They are still forming right now. There are also dark streaks on the surface, aligned in the same direction, suggesting persistent wind patterns. There are intricate valleys and canyons, some hundreds of kilometers long. There are plains of darker, reddish material. A region informally nicknamed Cthulhu Regio, after the Lovecraftian monster. A vast, dark whale shape curving around Pluto's equator. The darkness of Cthulhu comes from organic compounds called tholins. Complex molecules formed when nitrogen and methane in the atmosphere interact with ultraviolet radiation from the sun and cosmic rays, producing a dark, reddish-brown gunk that settles onto the surface. Tholins are also found on several of Saturn's moons, and, in the atmospheres of worlds like Titan. They are sometimes called prebiological molecules, because they contain some of the raw chemical building blocks associated with life. And then there are the ancient riverbeds. Yes, riverbeds. In the northern polar region of Pluto, New Horizons detected what appear to be ancient channels carved by flowing liquid. Valleys and meandering paths that look eerily similar to river networks on Earth or Mars. The liquid that carved them was almost certainly not water, given that water is rock solid at Pluto's temperatures. The most likely candidate is nitrogen, which, at periods in Pluto's orbital history, when it swings closer to the Sun and its atmosphere thickens, might have been fluid enough at the surface to flow and carve channels. These networks suggest that Pluto has experienced dramatic climate change over its long history. Cycling between periods of thin atmosphere and thicker atmosphere as its orbit carries it closer to and farther from the Sun over its 248-year orbital period. The atmosphere itself was another revelation. Scientists had known since 1988 that Pluto had some kind of thin atmosphere, detected when Pluto passed in front of a distant star and the star's light gradually dimmed before it disappeared behind the planet. A sign of a tenuous atmosphere bending the light. What New Horizons confirmed was that this atmosphere was primarily nitrogen, with smaller amounts of methane and carbon monoxide, and that it extended much higher above Pluto's surface than anyone had predicted. A haze layer reaching 100 to 200 kilometers above the surface. And the color of that haze? Blue. Pluto's atmospheric haze is blue, for the same reason Earth's sky is blue, scattering of light by small particles in the atmosphere. Standing on Pluto and looking up, you would see blue skies, not the jet black of airless space. The complete picture that emerged from New Horizons was of a world far more complex, far more geologically active, and far more climatically dynamic than the dead, frozen ball of ice that had been assumed. As New Horizons project scientist Hal Weaver put it, New Horizons transformed Pluto from a fuzzy, telescopic dot into a living world with stunning diversity and surprising complexity. Section 7. Ice volcanoes and a hidden ocean. Even among all the surprises that New Horizons delivered, two of the most striking discoveries came not from what the spacecraft found on the surface of Pluto's familiar hemisphere, but from features that simply defied any prior explanation. Just to the southwest of Sputnik Planitia, at the edge of the Great Nitrogen Glacier, New Horizons cameras captured two enormous mountain structures, unlike anything seen anywhere else in the solar system. They rise from Pluto's surface with the general silhouette of volcanoes, great domed constructions with wide, deep depressions at their summits. But these are not volcanoes in any earthly sense. On Earth, volcanoes erupt molten rock, magma heated by the intense thermal energy in the planet's interior. On Pluto, where temperatures hover near the absolute baseline of the universe, there is no molten rock. There is no ordinary magma. What these structures appear to be are cryovolcanoes, cold volcanoes, volcanoes that erupt not with fire and rock but with water ice, in a slushy mixture of ice and whatever other compounds are dissolved in the liquid below. The larger of the two features is called Picard Mons, rising about 7 kilometers above the surrounding terrain and spanning approximately 225 kilometers across. The other, Wright Mons, is about 5 kilometers high and 150 kilometers wide, roughly comparable in volume to Mauna Loa in Hawaii, one of the largest active volcanoes on Earth. Both features have large, deep central depressions at their summits, somewhat like calderas, but different from earthly calderas in subtle ways that suggest a different formation process. A detailed study published in the journal Nature Communications in 2022 confirmed what many scientists had suspected. These features were formed by cryovolcanic processes. Multiple eruption sites over a large area had deposited enormous volumes of water ice, more than 10,000 cubic kilometers of the material, building up the hummocky, lumpy landscape that surrounds Wright and Picard Mons. The terrain in this entire region is covered in irregular hills and mounds, some 6 to 12 kilometers wide on average, that form when erupted material piles up and spreads across the surface, rather than the clean, directed flows you get from ordinary volcanoes. The absence of impact craters on and around these features means the cryovolcanism that created them occurred relatively recently in geological terms, within the last 1 to 2 billion years. The researchers who published the study were careful to note that they could not determine whether the cryovolcanism was still ongoing. It may have ceased long ago, or it may still be happening today. To erupt cryolava, Pluto needs heat. A small amount of heat from the interior must be reaching the subsurface, melting ice or keeping water in liquid form at depth, allowing it eventually to find its way to the surface, through cracks and vents. This seemingly simple requirement turns out to have enormous implications. It means that beneath Pluto's frozen surface, beneath the crust of nitrogen and methane ices, beneath the layer of water ice that forms the structural bedrock, there may be liquid water. Not frozen water. Liquid water. An ocean. The evidence for Pluto's subsurface ocean has been accumulating from multiple directions. The location of Sputnik Planitia is one piece. true polar wander, the reorientation of Pluto's spin axis implies that the ice shell above a subsurface ocean can deform over time in response to unequal mass distributions, something that only makes sense if the shell is floating on a liquid layer. Computer simulations of Pluto's interior structure have suggested that a subsurface ocean is not only possible, but likely, and that it has probably been there for billions of years. A study published in 2019 by researchers from several Japanese and American institutions proposed a mechanism for keeping this ocean liquid despite Pluto's enormous distance from the Sun. Their simulations suggested that a layer of gas hydrates, clathrate hydrates, which are crystalline structures where molecules of gas are trapped inside a lattice of water ice, could exist between the ocean and the outer frozen crust. This layer would act as an insulating blanket, preventing heat from escaping upward rapidly enough to freeze the ocean. The most likely candidate gas for the clathrate layer is methane, abundant in Pluto's interior from the decay of organic materials in the rocky core. Then, in May 2024, researchers publishing in the journal Icarus added another detail to this picture. Using mathematical models based on New Horizons data, they calculated the density and salinity of Pluto's likely subsurface ocean from the pattern of cracks and deformations in the crust around Sputnik Planitia. Their findings: Pluto's ocean is probably about 8% denser than seawater on Earth, slightly saltier, similar in composition to the Great Salt Lake in Utah, and in a detail that is somehow both prosaic and wonderful. If you could somehow teleport to the bottom of Pluto's ice shell and find yourself floating in this hidden ocean, your body would float easily in the slightly salty, slightly denser water. You would be buoyant. There is liquid water in the depths of Pluto, an ocean hidden beneath hundreds of kilometers of ice, sitting in darkness and near perfect cold, insulated from the vast freeze of the outer solar system by a layer of crystalline methane gas hydrate. This ocean has probably been there since early in Pluto's history, possibly since the very formation of the solar system. It has been there in the dark, patient and still, for 4.5 billion years. Whether anything lives in it is a question that current science cannot answer. The conditions are harsh by any standard: very cold, very dark, cut off from sunlight and from the chemical energy gradients that life on Earth relies on near hydrothermal vents. But the discovery that Pluto has a liquid ocean at all has expanded our understanding of where in the universe liquid water can persist. If Pluto, at the frozen edge of the solar system, can maintain an ocean, then the universe may be far more full of liquid water than anyone previously imagined. And wherever liquid water exists, the possibility of life, however remote, cannot be entirely dismissed. The universe, as Pluto has taught us, contains surprises, and we haven't found the last of them yet. Section 8. Pluto's Moon Family. Charon and the Four Wanderers. No tour of Pluto would be complete without meeting its family. Pluto is orbited by 5 known moons, and together they form one of the most unusual gravitational systems in the solar system. At the center of this system, inseparably linked to Pluto itself, is Charon. We've met Charon before in this story, discovered in 1978 by James Christie, revealed to be roughly half the diameter of Pluto, its existence transforming our understanding of Pluto's mass and size. But what New Horizons revealed about Charon in 2015 was even more remarkable than its mere existence had suggested. Charon is about 1,212 kilometers in diameter, just over half of Pluto's 2,376 kilometers. This makes the Pluto-Charon ratio the most extreme of any planet-moon pair in the solar system. No other planet has a moon so large relative to itself. For this reason, astronomers sometimes describe Pluto and Charon not as a planet and a moon, but as a binary dwarf planet system. Two objects in mutual orbit around a common center of mass that actually lies between them, slightly above Pluto's surface, rather than within Pluto itself. The two bodies are tidally locked to each other. Each always presents the same face to the other. Unlike the Moon, which shows the same face to Earth while Earth rotates freely beneath it, Pluto and Charon keep the same face to each other in a permanent, frozen gaze. From the Charon-facing hemisphere of Pluto, Charon hangs in the sky enormous and motionless, never rising or setting, just sitting at the same point in the heavens while stars wheel slowly around it. From the far side of Pluto, Charon is completely invisible, never appearing above the horizon. What Charon looks like close up was one of the great revelations of the New Horizons flyby. The Moon has a distinct, deep red North Pole. A dark reddish cap, officially named Mordor Macula, whose color comes from tholins deposited from material that has escaped Pluto's tenuous atmosphere and been captured by Charon's gravity. It's essentially the chemistry of Pluto's atmosphere being painted onto its largest moon's polar region, slowly, over geological time. Charon also has enormous geological structures. A canyon system near its equator is estimated at 7 to 9 kilometers deep and stretches roughly 1,600 kilometers across the Moon's surface. A system of chasms and valleys proportionally far larger than the Grand Canyon, comparable to the Valles Marineris on Mars, and the southern plains of Charon, called Vulcan Planitia, appear to have been resurfaced in the distant past by cryovolcanism. Flows of ice water slurry that erupted from an ancient internal ocean, spreading across the surface and freezing in place. The formation of Charon is thought to be similar to the formation of Earth's own moon. The leading theory suggests that early in the solar system's history, roughly 4.5 billion years ago, a large object, perhaps a proto-Kuiper belt body of comparable size, collided with proto-Pluto at relatively low speed. The collision was violent enough to tear material from both bodies and fling it into orbit around the surviving larger object, where it coalesced under its own gravity into Charon. The smaller moons, Styx, Nix, Kerberos, and Hydra, likely formed from the same collision debris, smaller chunks of material that never coalesced into a large body. These 4 small moons are strange in their own right. Styx and Kerberos are tiny. Styx is only about 7 to 12 kilometers across, barely qualifying as a moon at all. Nix and Hydra are somewhat larger, roughly 40 to 55 kilometers on their longest axes, elongated and irregular in shape. None of them are spherical, lacking the mass to pull themselves into a round form under their own gravity. What makes the 4 small moons genuinely unusual is their rotational behavior. Unlike most moons in the solar system, which keep one face pointed steadily toward their parent body, Pluto's small moons rotate chaotically. They tumble, they wobble, their rotation rates and orientations change unpredictably over time, driven by the complex gravitational interaction of orbiting a binary system rather than a single body. The gravitational dumbbell formed by Pluto and Charon creates a constantly changing field of forces, and the small moons rock and spin in response. This chaotic tumbling had been predicted theoretically before New Horizons' arrival, but seeing it confirmed was another small delight in a mission full of them. The 4 small moons also orbit in near resonance with Charon. Their orbital periods are roughly in ratios of 3:1, 4:1, 5:1, and 6:1 with Charon's period. This near resonance is thought to be a product of the system's formation and subsequent evolution, as Charon migrated outward from Pluto in the aftermath of the Great Collision, sweeping the smaller moons along with it in resonant capture. The entire Pluto system is, in miniature, a kind of laboratory for understanding how binary systems work, how 2 roughly equal objects orbit their common center of mass, how smaller bodies orbit and tumble in the gravitational field of such a pairing, how collision events in the distant past can shape the architecture of a system for billions of years. It is complicated and dynamic and beautiful in its way, this small family of worlds at the edge of the solar system, going round and round in the darkness with nobody watching for most of their long history. Until July 14th, 2015. When we finally looked. Section 9. The deepest question. Is Pluto a planet? The debate over Pluto's planetary status didn't end with the IAU vote in 2006. If anything, the revelations of the New Horizons mission in 2015 revived and intensified it, because the Pluto that New Horizons revealed was so obviously, undeniably, a world in its own right, a geologically complex, atmospherically active, oceanically endowed body that bore no resemblance to the kind of dead, inert object that might reasonably be called something lesser than a planet. Alan Stern, whose fury at the 2006 decision had never really faded, became one of the most prominent voices arguing for reclassification. Stern's objection was not sentimental, it was scientific. He argued that the IAU definition was fundamentally flawed because it classified objects based on where they are in the solar system rather than what they are. Under the IAU's definition, an Earth-sized body orbiting at the same distance as Pluto would not be a planet because it couldn't clear its neighborhood any more than Pluto can. Conversely, a tiny asteroid in a special orbit might theoretically qualify. The definition, Stern argued, asks the wrong question. In 2017, a paper published by Stern and colleagues proposed an alternative definition based on geophysics rather than orbital dynamics. Under their proposed definition, a planet is a substellar mass body that has never undergone nuclear fusion and that has sufficient self-gravitation to assume a spheroidal shape, regardless of its orbital parameters. In plain language, if a body is large enough that gravity has pulled it into a roughly round shape, it's a planet, regardless of where it orbits or what else it shares its orbital region with. Under this geophysical definition, the solar system has a great many more planets, over 150, including Pluto, Eris, Ceres, and dozens of other Kuiper belt objects, as well as large planetary moons like Ganymede and Titan. Proponents of this definition argue that it reflects what the objects actually are, physically and geologically, rather than making arbitrary distinctions based on where they happen to orbit. Opponents of reclassification, including Mike Brown, who has written a book titled How I Killed Pluto and Why It Had It Coming, argue that the dynamical definition is scientifically meaningful precisely because it distinguishes between the 8 bodies that gravitationally dominate their orbital zones and the swarm of smaller objects that orbit in shared, crowded regions. The solar system, Brown argues, makes much more sense if you understand there are 2 fundamentally different kinds of objects in it: the gravitationally dominant planets and the vast population of smaller bodies that orbit in communities. Both arguments have merit. Both reflect genuine, thoughtful scientific reasoning. And this is perhaps the most honest thing that can be said about the Pluto debate. It is, at its heart, a dispute about classification, about the language we use to describe reality, rather than about the nature of reality itself. Pluto hasn't changed. Its mountains are still there, rising from their nitrogen glacier in the permanent twilight of the outer solar system. Its hidden ocean is still sitting in the dark beneath hundreds of kilometers of ice. Its cryovolcanoes are still, possibly, building new terrain. The question of whether we call it a planet or a dwarf planet is, in the end, a question about where we draw a line in a continuum. And continua don't care about our lines. The universe doesn't organize itself into categories for our convenience. We impose our categories on the universe, and sometimes the universe resists categorization. What seems beyond dispute, regardless of which definition you prefer, is this. Pluto is a world. It is complex, dynamic, ancient, and surprising. It has weather. It has seasons. It has mountains and glaciers and oceans and volcanoes. It has a family of moons, the largest of which is so big that they orbit each other as equals. It has a blue sky. It has red snow, crystallized methane falling from the upper atmosphere to dust the peaks of its water ice mountains in a slow, continuous frost. It has an interior that is still, 4.5 billion years after formation, generating heat, a heartbeat of radioactive decay keeping its hidden ocean liquid against the cold of the outer solar system. The New Mexico legislature was in some ways right. Pluto will always be a planet, in the way that matters most. It is a world, fully realized, with its own geology and its own climate and its own history stretching back to the birth of the solar system. It is not the 9th planet that it was claimed to be in 1930. But it is something more interesting than that. It is the king of the Kuiper belt, the first discovered member of the solar system's third zone, a world that waited 90 years for humanity to visit, and then astonished us when we finally arrived. Whatever we call it, Pluto is extraordinary. Conclusion. And so we've come to the end of our journey, drifting slowly back from the frozen edge of the solar system, from Pluto's nitrogen glaciers and its blue skies, and its hidden ocean of slightly salty water sitting in the dark, beneath hundreds of kilometers of ice. Let yourself grow heavier now. If you've been listening with your eyes open, let them close. If they've been closed this whole time, let your breathing slow a little more. Let each exhale take you a fraction deeper toward sleep. Think, if you like, about what we've covered tonight. The young farmer's son in Arizona, peering through a blink comparator on a cold February afternoon, seeing something move that shouldn't have been moving, and understanding in that moment that he had found a new world. The 11-year-old girl in Oxford, eating breakfast with her grandfather, offhandedly naming a planet over toast. Think of New Horizons, that piano-sized machine launched on a cold morning in Florida in January 2006, accelerating to 47,000 miles per hour, and then settling in for 9 years of quiet travel through the darkness of the outer solar system. 9 years of patience before those first blurry images began resolving into something unrecognizable and wonderful. Think of the heart. That great, luminous heart on Pluto's surface, 1 million square miles of convecting nitrogen ice, so massive that it pulled the planet's spin axis toward it like a compass needle. Pluto, physically rearranging itself around the weight of its own glacier. Think of the volcanoes that erupt not with fire but with water. Slow, cold eruptions of icy slush building mountains 7 kilometers tall. Morphologies unlike anything else in the solar system. Think of the dunes made of methane ice forming right now in this century, in the thin wind of a world 3 billion miles from the sun. Think of the hidden ocean. Down there in the dark, beneath everything, a sea of slightly salty water that may not live in it, it is there. Liquid may not live in it, it is there. Liquid water at the edge of the solar system, waiting. The universe is full of such surprises. We go to the places we think we understand, and we find that we understood nothing. We go to the places we think are dead, and we find life, or at least the conditions that might allow for life, which is not so different. We look at a small dot of moving light on a photographic plate, and we name it after the god of the underworld, never suspecting that underneath its frozen surface, in the cold and the dark, something resembling a sea is quietly moving. There are 8 more dwarf planets in the outer solar system awaiting deeper exploration. Eris and Haumea, and Makemake and Sedna and Quaoar and Orcus and Gongong and more waiting to be named. There are millions of Kuiper belt objects we thought to haven't visited. There are the distant reaches of the Oort cloud, a vast spherical shell of icy bodies extending perhaps a quarter of the way to the nearest star, from which long-period comets fall inward toward the sun over timescales of millions of years. There are other solar systems, other Kuiper belts, other worlds at the edges of other stars that are cold and patient and waiting to be found. We are still so early in the process of understanding the solar system we live in. We are still, in the cosmic sense, very young explorers. But we are explorers. We always have been. And the universe keeps rewarding that impulse, keeps showing us that where we expected emptiness, there is wonder. Where we expected death, there is geology. Where we expected a frozen stillness, there is a beating heart of nitrogen, and beneath it, an ocean. So, as you drift now towards sleep, let that be the thought that carries you. The universe is richer than we know. Every dot of light in the night sky is a sun with worlds circling it, and those worlds have histories and weather and possibly, things living in them. And even the small, cold, reclassified dwarf planet at the edge of our own solar system turned out to be astonishing, turned out to be alive in its own geological way, turned out to be more beautiful and more complex and more worthy of our attention than anyone had imagined when they looked at a moving dot on a photographic plate in 1930 and said, "We've found something new. You've traveled a long way tonight, 3 billion miles and more. Rest now. Let your breathing carry you further out, into the dark, into the quiet, into whatever dreams are waiting for you at the edge of everything. And if you enjoyed traveling with us tonight, please take just a moment before you drift away to leave a like on this video. It helps the Science Pillow reach other people who might be lying in the dark right now, wondering about the same things you wondered about tonight. And if you'd like to come back, to visit black holes and deep ocean trenches and the history of the first stars and the chemistry of your own dreaming mind, then subscribing is the way to make sure we're here waiting for you. Sleep well. Dream of oceans hidden under ice. The universe is kinder and stranger than you think.